All right, thank you for viewing our presentation today. We're excited to share with you. We're Justin, Michael, and Colin, and we chose to optimize the shape of a wing on a wind turbine to maximize power output. So we'll walk you through methods and results. To help you understand the problem a little bit better, here's the schematic. So we chose to idealize the wing shape as an ellipse. And that A is what's called the major diameter in an ellipse. And in a wing, that's known as the chord length. So that's the distance from the leading edge to the trailing edge. And the bigger that is, the more lift and more power you can get out of a wing. So we wanted to make A as large as possible while minimizing B. But the crux of the situation is that B needs to be large enough to prevent the hollow tube of the blade from buckling or breaking, either in tension or compression. So we want to maximize A and make B just big enough to withstand all the stresses. And some of the given things in this problem were things like wind velocity. We chose to use maximum wind velocity to make sure that the wing wouldn't break under the maximum conditions, and other things like material and the distance between cross sections that we were optimizing for. So there's two major assumptions we made. The first is that an ellipse is a good approximation of wing shape, which according to our research, it said that it was. And the second is that major diameter or chord length of a wing is directly related to the lifting power a wing can produce.
So to walk you through the model that we created, this diagram helps illustrate what those cross sections look like along the blade. As you can see, there are several elliptical cross sections that extend throughout, and they're evenly spread apart by a distance labeled dx here. And then at the base, it's connected to the wind turbine. It's assumed to be a circular cross section, which is normal for most wind turbines. And then we are able to adjust the number of cross sections that we would want in the optimization problem. And so we can determine the number of cross sections, and then also all of these inputs, A, B, and DX, will be optimized in the optimizer. So here's also what the model looks like. We basically assumed that the wind turbine blade was taken at a snapshot in time, directly when that wind turbine blade was vertical and facing down. So it's technically still in motion, but by taking the snapshot vertically here, we're able to eliminate some of the stresses due to gravity if it were taken somewhere else. And we also believe that this is going to be at a time where stress is very high. But as you can see, the stresses are all due to bending stresses because of drag and lift, and then also due to gravity in the longitudinal direction. And so by doing so, we used a simple constrained optimizer in MATLAB, and we were able to obtain a full profile of what the fin would look like based on this optimization. And we just had to continue to decrease the number of cross sections until we could get a good optimization. You'll see one problem we ran into was with too many cross sections, the optimization couldn't converge. And so this is how we set it up. One big assumption that we had here was that the stress was going to be at a max in this position, which we don't know if that's really true, but that's what we went forward with.
All right, I was really excited. We were really excited when we started getting results because as seen, the fin geometry looks to be rather close to the ones that we had in our picture, the ones that we had assumed that we were going to get, which is great. Originally, the problem that we had put into it was a little bit suboptimal. We had tried to only improve the cross-sectional area total of the fin, which was a huge issue because all of the cross-sectional areas were kind of just centralized around the very base of the fin, just to try to get as small stress as possible while increasing the area. And then once we started treating it a little bit more like a moment it actually gave a much better distribution, making it a lot more fin turbine-like, which is kind of nice. Listed is a table of all of the different the chords and the stresses shown at each of these radial locations. And so you can see that the stress max is still seen at the very base of the fin, but it does not exceed the maximum stress of the material that we had chosen. All right, this is the optimization, and I guess the convergence of the optimization. It took about 880 function calls in order for it to optimize, which is a lot of function calls. This is a very taxing optimizer based on all of the function calls that we had. So it, yeah.
Also, in consideration with this, we understand there are a lot of limitations to the model and the optimization that we did. So here's just a few of those big ones that we wanted to touch on. The first one was we had to force the optimizer to make each cross section a little bit smaller than the previous one as you go along the wind turbine blade. We found that if we didn't, that it would localize large areas at either the base of the wind turbine blade close to the wind turbine or way at the end of the tip. So that solved that problem. Another one was that we know that as the wind speed goes up, lift and drag go up, and we only solved for one wind speed. We don't know if this shape would be different if we had changed the wind speeds to higher than this max or something smaller. The other limitation was we only took it at the one snapshot when the wind turbine blade was directly vertical underneath. And that didn't account for potential bending stresses in the wind turbine blade when it is horizontal or in any other orientation that you can imagine. And the last one was because we had to use only a few cross sections, rigid the solution of that profile looks. And so we may need to, we would maybe need to improve the number of cross sections used to increase that resolution. But for now, that's the resolution we used.
So in conclusion, we all learned a lot about collaborating on technical problems and helping each other ask the right questions and figure out the smaller things that needed to be figured out to build up to the solving the larger optimization. We also learned about coding and collaboration and coordinating for things like that, as well as making appropriate assumptions based on sometimes not having as much information about the real world situation as you'd like. So those are a few of the things that we learned. And thank you today for viewing our presentation.